So here we're going to be applying Euler's theorem to a particular word problem or this scenario. So this one reads, many neighborhoods have homes equipped with electronic water meter sensors on the outside of the premises. The meters can be read remotely from a municipal worker's vehicle as they drive past the residence. Suppose the illustration shows several blocks of a neighborhood where residences are equipped with electronic meters. Determine an efficient route that a municipal worker would drive to read the meters. So here we have this little map here of this neighborhood with these roads. And what we're going to do is we're going to determine an efficient route. Now we have to kind of determine what is an efficient route. Well, we don't want to waste time or money or gas or anything like that. So maybe an efficient route would be where all the municipal worker would have to drive each street only once. If he's doubling back, that could take up time and that could use up money. So we're looking for where each street is only traveled once. Now we'll certainly use Fleury's algorithm to help us. And of course that algorithm relies on Euler's theorem. So maybe the first thing we'll do is we'll go ahead and we'll designate these intersections of these streets as vertices. You can see right here, this is Boole Boulevard and Gauss Avenue. So the intersections we'll treat as vertices, and then the streets we'll treat as edges. So there'll be a vertex here. There's 2, 3, 4, 5, 6, 7, 8, and it looks like we are going to have 10 vertices. And then, of course, the connection between the vertices along the road, those will be our edges. So we'll have one here. We'll have one here. This way. We'll keep going down Remond Street here down to Pascal Road. So we're just simply using the layout of the map, the schematic of the street map here to make our graph. Now since we're going to be using Fleury's algorithm, which relies on Euler's theorem, we're going to find the degree of each one of these vertices. This has degree 2. We have 2 edges that emanate from it. This is degree 2. This is degree 3. So that's odd. This one is even. And we forgot an edge right here. Let's put that in. So this one is even. This is even. This has 4. This is degree 4. Degree 2, even. Even. This one's also even. It's got 4 edges. This is degree 2, but this is odd too. This is degree 3. So this intersection right here and this intersection up here are both odd. So if this will have an Euler path. If there are exactly 2 odd vertices, it'll have an Euler path. And the path has got to start and end at the odd vertices. So if I start at this odd vertex, I got to end up over here, and vice versa. If I start here, I got to end up over here. So I'm just going to go ahead and I'm going to repeat this pattern over here. How about if I go 1, and it doesn't have to be to scale or exactly. It's just a condensed version of what's going on. Got this vertex here. I got one down here. Here, here, and then I have these 2 here. So if I start at this one here, this is one of our odd ones. That's this one right here. I can go 1, 2, 3, 4, 5, 6, 7, that's the street here. 8, 9, 10, 11, 12, and 13. So we started at this odd vertex and we ended up at this odd vertex. So the most efficient, or an efficient route, not necessarily the most efficient. There's several routes that can be taken, but it's an efficient route. Start here, follow this pattern, and we end up right here.